Okay.
Oh,
Okay. The
okay.
stage is yours.
Thanks very much for the invitation and for the very generous introduction. And it's really a pleasure to be presenting this work. Um, so I'm talking about saddle-to-saddle dynamics explains a simplicity bias across neural network architectures. It's joint work with my advisors, Andrew Sachs and Peter Latham, all at the Gatsby unit at UCL. And we will also be presenting it in ICLR this year in Brazil in April. Um, so I will just get started. So the reason that the general motivation that we study this problem is this um, general phenomenology and a number of standalone theories in deep learning about dynamical simplicity bias. So it just means neural networks with various architectures learn increasingly complex solutions over the course of training, manifesting in distinct stages. So maybe the earliest starts from 2014 of Sachs et al. That they observed linear dynamics, linear fully connected deep linear networks have these kind of stage-like learning dynamics where if you plot the training loss, it will really be very clean, just look like a stair. And later, people studied two-layer ReLU networks, and they also have these kind of stages in which the solutions they implement increases in complexity over time. And more recently, there is like quadratic networks, and there is also attention models that they also manifest in distinct stages during learning. Um, and so this is sort of like a fascinating phenomenon. And I also wanted to sort of mention that why we care about the learning dynamics of neural networks in the first place. I think it's becoming increasingly relevant because um, in the large language models era, we do not train models to convergence anymore. So maybe 5 or 10 years ago, every time we train a CNN or MLP, we train them to convergence and we use the model at convergence. And maybe then we had a good reason to just study the model at the end of training. But now none of the real models are trained to convergence, then we really care about dynamics because we use model here, we use the model somewhere there, and so we want to know that what are the intermediate solutions, and every time it goes a steps a stair, what are increments it is, right? What is the new thing that you learned at each transition? So the question we ask and try to answer in this work is that is there a universal mechanism driving the dynamical simplicity bias or a collection of architecture specific mechanisms? And another one question is how do we define simplicity and how does the architecture participate in this definition? Because when we say neural networks learn solutions of increasing complexity, sort of intuitively, it makes sense, but we don't really know what it means, or we don't know how to use this intuition until we give simplicity a really concrete and specific definition. And somehow the architecture should participate in this definition because it should reflect the fact that certain tasks are easy for one architecture that might be hard for another. Okay, so these are my two questions, and I'm just going to tell you the answer right now in case I've lost everybody at the end of this talk when I get to these answers. So first of all, is there a universal mechanism driving the simplicity bias? Do I need four theories for these phenomenon, or do I just need one theory? And the answer is there is a universal mechanism called saddle-to-saddle dynamics driving all these phenomena seen in the literature. And saddle-to-saddle dynamics just means every time the loss plateaus, it's because the gradient descent is approaching a saddle point on the loss landscape. And we'll get into a lot of detail what that means. And second question is, how do we define simplicity? And here we define simplicity as being expressible by that architecture with few units. So it's like every time you go through a stair, it's the effective expressivity or the effective width of that network increases. So to be more concrete, basically it sort of works here. So if you test the model at this stage, the solution that the model implements at those times is can be represented by that architecture with just 0 unit in linear network, zero hidden neurons, which is a constant function. And here it's 1, 2, 3, 4 hidden neurons. And for linear networks, a linear network with one hidden neuron can represent a linear map up to rank 1, and then up to rank 2, up to rank 3. And that is exactly what's happening in the deep, fully connected linear networks. It's learning solutions of increasing rank, and it's sort of can be explained by learning solutions for increasing effective width. And in ReLU networks as well, basically, if you test the model here, it can be represented by 0 ReLU neuron, 1 ReLU neuron, 2 ReLU neuron. And for ReLU networks, when you have 1 ReLU neuron, you can express input-output map with just 1 kink. Sort of, you can bend somewhere in your input-output space. And if you have 2 ReLU neurons, you can sort of bend in 2 places. It's like, so they learn solutions of increasing kinks. And for quadratic and attention, it's as well, it's their learning solutions that can be expressed with 1 attention head, 2 attention heads, 3 and 4. Okay, so this is how we define simplicity as the effective width or the effective expressivity of that architecture, and it sort of fits all the prior literature that in the previous slide fit into this definition. Okay. So I also have a cartoon to show you so that you have hopefully have a mental picture of what the neural networks are doing when we go through the theory. So let me see, where is my cartoon? Right. Okay. So I have a cartoon lost landscape. So it's sort of a 2-dimensional weight space, as you can imagine, as the XY axis, and the vertical axis is like the height of this surface represent the value of the loss at that weight. And my orange ball is doing gradient descent here, and I start somewhere at the top of this lost landscape, which is actually very small initialization, so it's very near 0, 0. And the gradient descent ball falls like rightward direction and approaches a saddle point, and then it lingers there for a little bit, and then it falls off in the, like, I don't know, towards us direction. And if you plot the loss for this dynamics, which is basically the height of this orange ball, it will just look like 2 stairs, right? It's the first plateau corresponds to lingering, sort of the time it takes to escape the unstable fixed point at the top of the lost landscape, and then it's like drops rapidly to the saddle point, and it lingers there for a little bit, corresponding to the intermediate plateau, and then drops rapidly to convergence, which is the second stair. So this is sort of how I like conceptualize the saddle to saddle dynamics, and I sort of want to say that the usefulness of conceptualizing the problem with this picture actually relies on mathematical facts that are common to many architectures that are not like specific to those architectures, because you might think like, okay, this cartoon just looks like quite artificial, and surely the ReLU network or the tension has like more complicated or like weird looking lost landscapes, and then why is it reasonable for me to imagine their dynamics with that cartoon? But it turns out that the picture, the usefulness of that picture relies on the facts that are common to those architectures, that are not specific to those architectures, and we will see why. All right. So I'm going to first introduce the theory, and then after that, try to make some predictions from the theory, so to see the implications of that. So to introduce the theory, also feel free to interrupt me anytime if you have questions. Okay, so I'm going to first introduce some notations to establish the theory. So first of all, we are going to. Oh, okay, better after. Okay. So we use f of x to represent a neural network with input x, and we're just going to focus on one layer inside that network with h units and trainable parameters theta1 to theta h. So my network is g out, this thing, which is this layer that we're trying to study. So you can see the g out and g in are like the processing before this layer and after this layer, which are usually the shallower layers and the deeper layers inside the network. and we're just going to focus on one layer inside that network that has like width h, and sort of the UI is like the incoming weight, the input weight, or the first layer weight of that layer, and the UI is like the second layer weight with a readout weight of that layer. And theta I is just, I call the concatenation of the trainable weights in that unit, which are just VI and UIs. So this definition is actually quite general. Incorporates the fully connected, the convolutional, and the attention-based architectures, and sort of it's obvious that this can't be fully connected layer, right? This if you just set phi to be the weights times the input going through some activation function sigma, which can be I don't know, sigmoid or ReLU. You can also add a bias term here. It will just be a fully connected layer, right? I call this G in thing Z, the input to that layer. So this if you let phi to be this, this would obviously look like an MLP layer or a fully connected layer. And the convolutional layer can also be written in this way if you let phi to be like U convoluted with the input Z and going through some activation function. So so the U here then would just be the convolutional kernel weights, right? And maybe the least obvious one is that the self-attention layer also falls into this definition. So basically, usually when we write self-attention, we write value weight and then input, which here we call Z, and then softmax of attention matrix, right? The attention matrix is input sequence times key weight times query weight times input sequence. So basically, I call this thing V, right? And I call this entire thing my phi Z, which U here is the trainable weights in this thing is my key and query weight. And so this is sort of like a funny looking activation function because it has the input repeated 3 times and going through and softmax and times the weights and something. I write it in, and I realize that this is not the usual or common way than how we write and understand self-attention layer, but I wanted to write it in this way just to show you that the attention layer also falls into this definition in the first equation. Okay, so now that we have seen that the fully connected layer, convolutional layer, and self-attention layer all fit into this definition, it means that whatever statement we're going to make about this first equation is going to apply to fully connected layer, convolutional, and self-attention layer. And we're just going to train the parameters with gradient flow. So that's theta dot, which is theta d theta dt, is going to be the negative gradient of loss with respect to the parameters. And we call set of weights the fixed point of the gradient flow dynamics if the gradient of a loss evaluated at that point is 0. Okay, so we now have all the notations we need. We can introduce the theory now, and we're going to introduce the theory in 3 steps. So first, we're going to show that saddles generally exist across architectures. And second, invariant manifold generally exist, and they connect pairs of saddle points. And the third step is to show in certain architectures, gradient descent will naturally follow the connecting paths between saddles like repeatedly and pays visit to those saddles one by one, and the dynamics would be saddle to saddle. Okay, so for the first part, we're just going to show that saddles generally exist across those architectures. So basically, I have, for this cartoon lost landscape, I paid visit to these 3 saddles, right? And there are actually more. I didn't draw them. So here is one, here's one, here's one, here's one. So maybe 9 in our horizon. And so why are there saddles in all these architectures? And the reason is actually really simple. And okay, so this sentence is a bit long, but I promise that the reason is really simple. So this theorem says, if a network with h-1 units has a fixed point theta star 1 to h minus 1, and it yields the input of math f star x, then there must exist a set of weights such that a network with h units, so just one more unit wider, implement the same input of math f star x, and theta 1 to theta h is a fixed point of that 1 unit wider network. And the reason how and how we do that is actually really simple. I'm going to show that with just like, say, a really simple neural network. Let's say we start from h equal 2. So I have a network with just 2 neurons. So units here, I use the word unit because for fully connected layer, it means hidden neurons. For convolutional networks, it means a convolutional kernel. And for attention layers, it means a head. So they are 3 different words. So I just chose a 4th word, unit, to incorporate all of them. But it's basically the width. So let's see, I have a network, let's see, with, yeah, like 2 neurons. And so this is the input, this is the output. And as our definition, I call the incoming weight the U's, U1, U2, and the outgoing weights V1, V2. And now I'm just going to construct a 1 unit wider network such that it should implement the same input map, and it should also be a fixed point. And basically how I do that is, let me just copy this. Okay. And I want to add 1 more unit to it. So I add the 3rd unit and going to change the weights a little bit. So basically I'm going to set the incoming weight of the 3rd added neuron to be the same as the 2nd one. So I have U2 here as well. And for the 2nd layer weight, I'm going to scale the 2nd layer weight of the 2nd neuron by a constant, say alpha U2. And we're going to let the 2nd layer weight of this additional neuron be 1 minus alpha time. Oh, sorry, that's V. V, okay, V2. Okay, so basically I split the 2nd neuron into 2 parts. And because of that, it's sort of obvious to check this condition, right? This h equals to 3 network implements the same input of math as this h minus h equal 2 neuron. So this part is checked. And this part is also checked with a little bit of math. So if this set of weights is a fixed point for the h minus h equal to 2 network, it should be the case that these set of weights is also a fixed point for the h equal to 3 network, because of mainly I'm like copying the weights and rescaling the weights. So if you do a little bit of math, you will see that the gradients of these weights are either equal or proportional to the gradients of this network. So if these weights have 0 gradients in this h equal to 2 network, these weights are also going to have 0 gradients for this slightly wider network. And right, so this should be sort of straightforward, that you can see you can always embed a narrower network solution into a wide network. And if the narrower network solution is a fixed point of that narrow network, that embedded solution in the wide network is also going to be a fixed point. And it should also sort of be straightforward that you can do this like many, many times, right? You can embed the h equal to 2 solution all the way to 1,000 or 10,000 if you want, just by do this kind of repeated splitting. And this means that no matter how wide your network is, you always have these kind of really simple solutions being fixed points of that wider network. And those simple solution fixed points are like the fixed points, or like even the global minimum of the really narrow network solutions. So because your width 1 or width 2 network always has a global minima, which are fixed points of that really small network, you can embed that into a really wide network, so that really wide network would have some really simple solutions being their fixed point. And sometimes, well, the reason is not clear at this point, but sometimes they visit those simple solution saddle points during learning. Okay, So yeah. Oh, I also wanted to mention that this original idea of embedding narrow network solutions into wide network was discovered by Fukumizu and Sunchi Amari in 2000. So 26 years ago, they're way ahead of their time, and it was a brilliant idea. Um, so um, they've come up with the original idea of embedding narrow solutions in a wide network. And the thing we do, building on their work, is to came up with a few more ways to embed the solutions of narrow network in the wide networks, and also more importantly, we study the saddle-to-saddle dynamics of these embedded fixed points and connect to simplicity bias. Okay, and right. So basically, the whole theorem goes as a list. The thing that I just told you is this one. It's like the simplest or the most general way to embed a narrow. Oh, you don't have to read this. So I told you number one, which are like the most general way for any phi, any horrendous activation function, you can embed the narrow solution to a wide network. And these are just like if you know more about the activation phi, there are actually more ways that you can do this. So, for example, if phi is homogeneous in U, which are like ReLU, you don't have to copy. So here I copy the first layaway. If it's homogeneous, you can actually rescale the first layaway as well. Rescale. So here I only rescale the second layaway, but in ReLUs you can rescale the first layaway as well, and sort of believable because ReLU is homogeneous. And if phi is linear, you can not only rescale the weights, you can even add and subtract weights because, well, linearity is about adding and rescaling, right? Right. So these are a set of ways that we show that how you can embed the narrow network solutions into a wide network and remain those solutions remain fixed points of the wide network. And so we've shown that and because we didn't use any specific properties of any specific architecture, this sort of method works for the fully connected convolutional or attention networks, and they will all have this sort of fixed points. And the first part is established that saddles generally exist across those architectures. And the second step of the theory is to show that we have invariant manifolds connecting pairs of saddle points. And so invariant manifold of a dynamical system, so here a gradient descent dynamical system, is a manifold such that any point starting on it remains on it under the system's evolution. So these are actually the cyan curve and the yellow curve I'm drawing here. Those are actually invariant manifolds. So basically, if you start anywhere exactly on the cyan curve here, it will just the gradient descent ball will be constrained to only move within the cyan curve forever. It's not able to explore anywhere else on a lost landscape. So you're gonna just like move this way, and it cannot go anywhere else. Well, this one can because it's not exactly on the manifold. It's like approximately on it, so it's gonna stay on it for a while and then do something else. But we're for now only concerned with the exact thing first. Let's see why these things are invariant manifolds. So the point is also very simple, or maybe even simpler. So in gradient flow dynamics, invariant manifolds always exist, and they correspond to weight configurations that make the network effectively narrower or simpler, according to our definition, than its actual width. And the really simple one, or almost trivial one, is that when two neurons, or when two units have equal weights. So if theta I equal to theta j, that's an invariant manifold. And you can sort of easily see that because, well, they're equal at some time point, which means they have the same initialization, and then they're going to receive the same gradient update at each iteration, so they're going to stay equal forever. And when you have theta I equal to theta j, that's a weight configuration that makes this network effectively narrower or simpler, because basically you cannot the effective width of the network, it reduces by one, right? Basically, I can just delete the jth neuron and rescale this ith neuron somehow, and it will be fine. So the width of the network when you have theta I to theta j is not its actual width. It's actual width subtracted by one. And similarly, I also have like a fuller list, which are just, if you know more about phi, these invariant manifolds are actually larger. So if it's homogeneous, then you don't have to be equal. You just need to be proportional, and they will stay proportional forever. And if you have a zero, basically you have a zero weighting some unit, they're going to be zero forever. And if it's linear, then you don't have to be proportional. You just need to be low rank. If it's exactly low rank, the weights are going to stay low rank forever. And this is about why they generally exist. And the point about why it connects those pairs of saddle points that we talked about just now is, I hopefully also sort of easy to demonstrate. So here, maybe like let's consider an example of a width 3 network again. And maybe this fixed point is a solution that can be represented with 0 unit, so like a constant solution. And this one is like a h equal to 1 solution, and this one is a h equal to 2 solution. And the Sion manifold is maybe an invariant manifold that has theta 1 equal to theta 2 equal to theta 3. So when you have theta 1 equal to theta 2 equal to theta 3, basically effective width of this network is like at most 1, right? So then this h equal to 1 solution is on that invariant manifold. And the h equal to 0 solution is obviously also on this invariant manifold. So basically this invariant manifold, it connects the h equal to 0 and h equal to 1 fixed point pair. And for the yellow manifold, we can exactly break just one equality. So let's say it's theta 1 equal to theta 2, but not equal to theta 3, right? And then it's the effective width of the network is at most 2. So then the h equal to 1 solution is on that yellow manifold, and the h equal to 2 solution is also on that yellow manifold, because you can use theta 1 and a theta 2 to be just one unit, and theta 3 will be another unit, and just it finds the best width 2 solution of that network. And so this invariant manifold, well, maybe not the equal to theta, not equal to theta, this invariant manifold connect the fixed point pair of h equal to 1 and h equal to 2. Right. So yeah, so basically the invariant manifolds always exist, and they connect pairs of these embedded narrow network solution fixed points. Okay. Right. Yeah, so basically the thing we established just now are like fixed points and invariant manifolds, but the missing part of this story, the yet missing part of this story at this point is that why does gradient descent follow those paths, right? Why does gradient descent pays visit to those saddle points? It's not necessarily the case they do that, actually. And what our statement is that in certain architectures, actually, under certain conditions, gradient descent will naturally follow the connecting paths between saddles iteratively and visits the saddles with increasing effective width or increasing complexity. And there are two necessary conditions for that to happen. And the first necessary condition is that the initialization is near an invariant manifold. So here, basically, my initialization is here. Yeah, my initialization is here. And it's sort of very near the Sion manifold. It's also very near a saddle point, although it doesn't have to be, but it is in this cartoon. And you can from this cartoon see why that is necessary, because what if I just start anywhere? I start here. Then I really I can't really make much statement about what the dynamics would look like. It'll probably not be saddle to saddle, because according to this cartoon, you're probably going to fall this way. So in order for it to follow these invariant manifolds and goes to saddles, the initialization firstly needs to be near an invariant manifold. And the second necessary condition is that escape path from saddle points need to match the invariant manifolds. And we can also see it from this saddle point. So basically, if I start here, the gradient is pointing, the sharpest descent direction is pointing sort of this way. And it matches the CI manifold direction. And you can imagine that it doesn't necessarily has to be the case if this loss landscape is sort of curved up in a different way so that it want to fall off this direction when it's initialized at this near the saddle point. It can be the case, right? And then it wouldn't go along the CI manifold and they wouldn't have saddle to saddle dynamics. But in this case, it actually satisfied that condition. Starting from this saddle point, the gradient is going to point this way and it's going to sort of follow the CM manifold and goes to saddle points. And this is sort of an inherent intrinsic property of an architecture that we need to concretely do some work to see whether the escape path, like with a small perturbation around a saddle point, does it follow the invariant manifold? And we will show for a certain concrete architecture it will, but it's not always the case. Okay, so right. So what I have said about saddle points and invariant manifolds, they apply to the general definition I gave in the beginning, which are like you can have a really deep network, and we just focus on one layer inside the network, and the embedded fixed point argument and the invariant manifold argument works for the deep networks. But for the dynamics part of this theory, I'm going to simplify and then consider a two-layer network because I need to work with a somewhat concrete architecture. And so in the following, we're going to study this expression. So basically, I dropped the G in and the G out. Okay, and I categorize the architectures into two categories, so that I call first order and second order. So they're higher orders as well, but the higher orders are similar to the second order. So I'm going to focus on the second order here. So the first order and second order, by that I mean whether the phi is linear or quadratic in the incoming weights u. So the first order architectures here, basically this part is my phi. So this is phi, I previously called that phi x ui. And this thing is linear in u. And it's sort of, we don't really care about whether it's linear in x or not. We just, for the purpose of this categorization, I just care whether it's linear in u. So here it's like u times some function of x. It can be just like u times x, which will be a linear network, but it also can be like ui convoluted with x. This would also fall into the first order category because you can sort of rearrange x such that this will be ui transpose some function of x. And the convolution is still like a linear function of the convolutional weights ui. And it can also just be like nonlinear in x as well. It just needs to be linear in u. And again, for the second order as well, this part is my phi. And you can see this phi is quadratic in u. And we don't quite care for this analysis whether it's this. It can have other dependencies on the input, but it needs to be quadratic in u. And so obviously quadratic networks falls into this definition, and linear attention also falls into this definition because in linear attention, so basically linear attention is attention without softmax, and then it is, I'm going to write this again. So this is linear attention. So I dropped the softmax here. This is linear attention. And this, for linear attention, this part is phi. U equals to k and q. So you can see this phi is quadratic in u, it's bilinear in k and q. It's quadratic in k and q concatenated, and it's cubic in in X. So basically the relevant Z of X for linear attention is going to be some cubic function of the original input sequence X. And we just sort of arrange the Z such that it will look like this general definition of a quadratic. Right, I wrote that just to show that the linear attention falls into the second order category. Okay, so for the first order architectures, which are linear fully connected networks and linear convolutional networks, and for the second order architectures like quadratic and linear attention, the mechanism for them, they all have saddle-to-saddle dynamics, but the mechanism for them to have saddle-to-saddle dynamics is sort of slightly different. And we're going to look at the first order phi first. So if you have a first order phi, the dynamics near a saddle point is approximately a linear dynamical system. So it's not immediately obvious. It is sort of needs a little bit of work, but you can show that if you have this kind of architecture, the dynamics near a saddle point is a linear dynamical system. So remember that I call theta I the trainable weights in the ith unit, so it's vi and ui concatenated. If you write down the dynamics near a saddle point, it is a linear dynamic system, so d theta dt is some approximately constant matrix times theta I. So this is like a textbook linear dynamical system, and it has a known analytical solution, which is exponential growth along all the eigendirections of A. So I call the eigenvectors of A, AK, eigenvalues of A, lambda K. So then this textbook linear dynamical system will have the solution of it's exponentially growing along all the eigendirections of A at a rate of the associated eigenvalue. So this is my eigendirection, this is my exponential growth or decay if lambda k is negative. And these are constants that initializations decide. And because exponentially growing along all the eigendirections of A, if A has distinct eigenvalues, it would mean that the top eigendirection grows faster than all the other directions, actually exponentially faster. And the gap is exactly the first eigenvalue subtracted by the second eigenvalue. And then it will mean that all the units grow along the top eigendirection. And it's coming from the fact that, if it's the case, it's because of the fact that the A have distinct eigenvalues. And because all the theta i's are growing along the same direction, it's a rank 1 weight growth. And for linear networks, rank 1 weights actually match an invariant manifold. And so basically for this kind of architecture, it checks the box of the escape path from the saddle points match an invariant manifold. And the relevant invariant manifold is the low rank weights for linear networks. Okay, so this is the analysis for the first order phi. And for the second order phi, it's a slightly different mechanism. So for the second order phi, the dynamics near saddle point is not a linear dynamical system anymore. It's a quadratic dynamics. And it's actually sort of complicated to solve the dynamics for this for this vector case with like vi and vector ui here. I'm not going to show that. So for intuition, I'm going to show like a really simple quadratic dynamics, or maybe the simplest possible quadratic dynamics. It has the same flavor as this this actual quadratic network case. So for intuition, we can just consider this scalar case, which is like maybe the simplest quadratic dynamics, which is a scalar d vi dt is vi squared. And with a little bit of work, you can show that the solution to this ODE is this. For one, you can check that you can sub t equal to 0 into this equation and it'll be consistent, right? It's like vi0 is vi0, so it's consistent. And this kind of quadratic dynamics, it blows up in the finite time. So if you plot t of vt, it's sort of with a small initialization, be very flat for a while and then suddenly increase to infinity, or all we care about is to a constant, to order 1 value. But if you keep on evolving forever, it will blow up. So and the blow up time exactly 1 over vi 0, as you can see from here, because it's in the denominator. And so this is for vi 0 to blow up. If you have vj 0, it'll blow up in a different time, right? It'll blow up in 1 over vj 0. And as long as the initial condition of vi 0 and vj 0 are not exactly equal, they're going to be this gap in their blow up time. And it will mean that there is some really lucky unit that's going to grow faster than all the other units. And it will mean that only a top single unit grows. And it's primarily coming from the fact that they just have distinct initial conditions. As long as their initial conditions are not exactly equal, there is going to be a time gap. And the single unit width growth also matches an invariant manifold. Oh, sure. Yeah, the single unit width growth is matching the invariant manifold of just one unit is having have non-zero weights and is evolving, and all the other weights are approximately equal and very near 0. And that's also an invariant manifold with the phi that has zeros. And so for the second order phi, it also checks the condition of the escape path from a saddle point approximately match an invariant manifold. I also just want to say that these are dynamics near a saddle. So when it's escaping from the saddle, the dynamics are not described by this ODE anymore, so it will not actually explode. But in the around a small perturbation near a saddle point, the dynamics approximately described by that. And we use that to show that there is going to be one lucky I. Just lucky means it has the largest initial condition. It will grow faster, it will run faster than all the other units, and it will look like only a single unit grows. And this is sort of the rich gets richer kind of dynamics that has many names across different fields. So in economics, people call that Matthew effect or preferential attachment. And here it's we also see that in neural networks. And we can sort of verify this very sloppy analysis. Well, to convince you that I'm not crazy. So this analysis is a bit sloppy, but if you see the if we do some simulations, we will see the difference sort of very clearly. I have those first order and second order architecture examples here. So here's linear fully connected networks, linear convolutional networks. They are the first order phi. And I plot the loss curve with respect to training epochs. You can see there is a stair. So across all these architectures, it has all saddle-to-saddle dynamics, and also plot the weights at the intermediate, during the intermediate plateau. So this weight is plotted at this time point, and this weight is plotted at the end of training. And I intentionally made the first layer weight UI two-dimensional, so I can plot it on a plane. And the width of this network is 50. So I plot U1, U2 all the way to U50 as every one of them as a dot. So basically there are 50 dots here representing U1, U2 all the way to U50. And you can see that they are rank 1 at the intermediate plateau. And they're scattered around, or rank 2 at the end of training. And the same case with linear convolutional networks that are rank 1 and rank 2. And so these are the first order phi. And for the second order phi, we see something different. It's so again, this is plotted at the intermediate plateau. This is at the end of training. So at the intermediate plateau, for these architectures, they're literally just one lucky unit that has left 0. All the other ones are still here. And at the end of training, there are literally just 2 units that has left 0. All the other 48 unlucky units are still very near their initialization at 0. And the same case with linear tension is 1 unit, 2 units. So this is kind of fun because if you just plot the loss dynamics, it all looks like staircases. So maybe they're all doing saddle dynamics. There's not a difference. But if you plot the weight dynamics, the weights are actually quite different. So this here, the weights increases in rank, and in this case, the weights are very sparse, and it's literally just 1 or 2 or 3 single units grows at each transition. And I have, I think, a movie version of this, yes, on the website. So you can, so this is basically the same thing, but played in video, and so you can see how the weights are rank 1 and then become scattered around, and in the quadratic network linear attention case, how it's sort of just only one thing pops out from 0, 0, and at the end of training, another thing pops out. And the middle column is a thing that I do not introduce in detail. It's a ReLU homogeneous kind of activation function where there's one ray of neurons growing at a time. Okay. Right. So I'm done introducing the theory, and I'm just going to go to the trying to draw some implications of the theory. And so the first thing is we can predict the effect of network width on the dynamics of these two different categories of networks. So for the first category, because all units grow along the top eigendirection, and it's coming, and the duration of this plateau is governed by the distinct eigenvalues of some sort of data statistics matrix. When I increase the width of the network, it doesn't really do much. It still sort of has the same range of plateau durations. But for the second order phi, when I increase the width of the network, it's going from dark blue to yellow, the plateaus are getting shorter to shorter, and it's can be explained by the analysis we just did, because the plateaus in the second order phi, in the case of second order phi, are governed by the gaps in their initial conditions, right? And when I increase the width of that network, I'm sampling more densely from the initialization distribution, and the gap between adjacent sample becomes smaller. And because that gap governs the plateau duration in this kind of architectures, when I narrow the gaps, I decrease the plateau duration in those architectures. So you can see a difference here. When I increase the width in this kind of architecture, it doesn't do much, but for these kind of architectures, the plateau gets shorter. And you can reason this, you can make this prediction from the analysis we just did. And the second thing is you can do the same for data distributions. So I draw the relevant data, relevant eigenvalues of the fixed, for these two, for these plots, I'm using depth 2. And you can do the same thing for the data distribution. So I'm controlling the relevant eigenvalues of the constant matrix to be following a power law. So this is the power law exponent, and I'm from yellow to blue decreasing the power law exponent, so making the eigenvalues more and more similar at power law exponent equal to 0, all my eigenvalues exactly equal. And you can see when that happens, I have no intermediate plateaus. And this is because the gaps in the eigenvalues govern the duration of the plateaus. If I make that gap disappear, it will make the plateau disappear for the first order phi. And for the second order phi, when I narrow the gap, it also has a fact of shortening the plateaus, but even at power law exponent equal to 0, there are still plateaus, because the distinct initial conditions of each unit is by itself enough to drive the time separations between the growth of each unit. So even when the data statistics are equal, there are still plateaus in the second order phi kind of architectures. And so those are with data distribution. Let me skip this. And for initialization, we can also predict that, as we were saying earlier, if you accept this setup, we sort of realize that the necessary condition for the network to have satisfied dynamics is initializing near an invariant manifold. So initializing near a saddle is actually not necessary to have saddle-to-saddle dynamics. And I did an experiment of initializing near an invariant manifold, but away from saddles. So basically, for this cartoon, I don't initialize here. I initialize like here, which are also sort of near the invariant manifold, but away from the saddles. And it will have this kind of exponential decay followed by sigmoidal drop kind of dynamics. And for linear, so this is linear networks. For that, it just invariant manifolds means low rank. So I'm using large low rank weights. You will have a really rapid drop at around initialization, and then subsequently, because it's going to the best rank one solution saddle point, and then subsequently have the similar to small initialization kind of sigmoidal loss drops. And this learning regime is perhaps not present in the prior literature. Okay. And similar things happen for large rank 3 to large rank 3. So basically, it will just like exponentially. I'm not sure it's exponential or not. Actually, it's just there's no plateau at the beginning. Rapidly goes to the rank 1 fixed point, and then takes a long time to go to find the rank 3 solution. And then if you use large rank 3, it's going to go to the global minimum really fast all at once. Okay, and I'm done here. So to summarize, we try to provide a theoretical framework that explains the simplicity bias for a class of neural networks, and by that we identify a mechanism behind the general intuition of that neural networks can decompose a task into smaller pieces and learn piece by piece over time. And the learning process in this regime reconstruct the network's own architecture, one unit at a time. And with that saddle-to-saddle dynamics, we dissociate the primarily data-induced and the initialization-induced saddle-to-saddle dynamics, and we use the theory to make some predictions of how the network width and data statistic initialization, both the scale and the structure of the initialization, how that affect the dynamics. And thank you for your attention.
Thank you very much. It was wonderful talk, and I like the attention.
Thanks.